Okay, so let's continue with our discussion. We talked about, we got started with, make sure, Schwarzschild Spacetime, and we discussed how it describes a spherically symmetric spacetime, and therefore one can conclude that it takes on this form. Oops, I always do the sine squared theta squared. And this part is the metric of a sphere. Okay? So what we're thinking of is, although there's no reason to think that that's what we're doing, but think, if you will, something like a star that creates a gravitational field. This is a spherical object, therefore that the field created would be spherical. Now suppose right over here, an observer is just standing. And he or she would measure proper time. We have seen, so suppose you have two observers. We have an observer here and another observer further away, two. We have seen that the proper time for these two are not the same. In fact, d tau 1 for weak, I mean, we don't know general relativity, so our assumption was very weak, plus delta change in gravitational potential energy over c squared. Yeah. We also know that in gravitational potential is minus gm over r for a spherical object. Same thing as in ENM, because it's kq over r, the electromagnetic potential. Here the gravitational potential is gm. Okay, so what we're going to do, we're going to assume that this guy goes all the way far back to infinity. At infinity, this becomes -1. Far away from a star, it's just vacuum, right? I mean, it's just Minkowski. Okay? So, and then what happens is, so you have delta phi becomes phi2 minus phi1, and that approaches, as r approaches infinity, r2 approaches infinity, because the second observer is going all the way to infinity, you would get 1 over infinity or 0. So this becomes just gm over r. I could put r1, well, let me put r1 over here. And therefore, we get that c squared d tau squared, again, approximately equal to 1 plus phi over c squared squared c squared dt squared. Why did I do that? Because this just becomes that, right? Oh, sorry, this is minus. So this is plus, this is minus. This is a stationary observer. You might wonder why I just put dt squared. For a stationary.
Is that one also minus?
I'm sorry?
That c squared d tau squared property, the one minus c squared, or should it be plus?
No. Yeah, that's the correction, right? It is, this is phi2 minus phi1. So minus of that is phi1 minus phi2.
Oh, and so it becomes plus phi.
Yeah, so, right. Let me make that very clear. I squished it all over here, I should say. As observer 2 approaches infinity, phi2 approaches 0, d tau 2 approaches dt. That's how you get this. See, I could make this c squared dt squared. I didn't have to write these terms. Why is that? Because the observer is stationary. So there's no dr squared, there's no dt squared. If you look at the world line of the observer is only getting older in time, if you will. Yeah? So all the other terms go to 0. Now, this is only true very weakly, like I said. We don't know anything about gravity. So whenever we try to take the lowest order term, when we square something, we carry errors. So for very small phi, if you Taylor expand, we want everything to the linear order phi. Well, actually, in this case, it's easy to do. Let's just do this. 1 plus 2 phi over c squared plus phi squared over c to the 4th. Which is the term that can be ignored?
Second.
Yeah, the second order can be ignored. Therefore, I can write this. I can make you write it as the next line. I would get ds squared is equal to this guy, which is now, I have to put a minus 1 plus 2 phi over c squared dt squared plus, well, I shouldn't say equal to. This is not a proof. I cannot prove this right now. This is just a motivation. How come when I went from there to here, I got a minus sign?
GTT would be the first index.
G, right. But remember, ds squared equals, or rather, do this. C delta tau equals the square root of minus g mu nu x dot mu sub ds. So when you square, it's the negative of that g. Yeah? This is just let me write this is equal to minus 1 minus 2 gm over c squared. Again, this is not a proof. I'm motivating a solution. Now, turns out, let me give you the exact answer. And it's as simple as that. ds squared. And this time, I want to say not approximately equal to. If when we study the full general theory of relativity, when we write the Einstein, we're going to do GR, but when you write the field equation, you will find that this is the exact solution. Look at this. All of this approximate, just hokey arguments together, right? Look at how nature works out. Equal to. How about that? All this is correct. Of course, I will write one term, right? I cannot motivate this at all at the moment. Forgot. This is the exact metric. The spherically symmetric metric to the full Einstein equation. We will derive this. Once we know the equation, it's easy to check, right? You put it on the left-hand side and you better get the right-hand side.
So GRR, no matter what your metric is, will always...
No.
Only at
Yeah, we haven't seen the... Oh gosh, life would be so much easier if that were the case.
Okay.
Nothing about the Einstein equation is easy. Unlike Maxwell's equations, these are nonlinear equations.
And so this is only ds squared forward when r is approaching infinity.
No. This is exact for a spherically symmetric spacetime. So now we're thinking the following. And we're not thinking correctly. That's all right. I don't necessarily want to think correctly. So you're thinking there's something over here, right? And that's the metric outside. And by our intuition, this is not wrong necessarily what we're thinking, but this object has mass m. And that's true, but it's something. Yeah? So there is something over here. Now, let's see what this might mean for the sun, and let's put a little bit of physics. So first of all, I'm going to use a simple notation, r star, just to get rid of all the that is this quantity. What would be the unit of that quantity? You can easily tell. If this is 1, this has to be 1. So if this is meters, what does this have to be? Meters. So it'd be meters over meters. Okay? So suppose I just want to, if I did this for the sun, meaning I put Newton's gravitational constant over here, speed of light over here, mass of the sun over here, I denote it like so. R star for the sun is roughly 3 kilometers. But if I take r star and then divide that by the radius of the sun, gosh, this is not a nice looking spherically symmetric object. When I want to, I don't think I can do any better. So if this is the sun, look at what happens. This is the sun. And this radius is the radius of the sun. This radius is r star. Oh, sorry, the other way around. And this is not to scale.
Yeah.
I mean, I mean, when I say not even the ratio, like this length is 1,000,000 more than that length.
Yeah. It's definitely not.
So it'll be a dot. I'm sorry. Go ahead.
No,
Go ahead.
I was just saying, we knew that you were talking about the drawing on the board was not to scale.
All right, fine. I know. But I had to say it. Just to have it on record.
Are you sure it's not a scale?
Don't want people to get confused, get the wrong idea.
So,
if you look up, it is about that size.
well, that's true. That's true. So whatever this r star is, it is very small. It is much smaller than, for the sun, for example, the r star would be way inside the sun. So if this describes the gravitational field outside the sun, that pretty much does. Yeah? We cannot get close to r star. Because in r star, there's a problem. So let me first of all call this, give it a name. Of course, we're going to call it what? The Schwarzschild? Yeah.
See the problem?
That's what we're going to call it. Yeah? What is the problem?
You start to.
When r equals approaches what?
It's undefined.
It's undefined.
Yeah.
Gosh, don't get so close. Yeah? And also, this is weird. So don't let time tick. We're just observing things, right? Just observing. We're not intuiting anything at this point. This would be the metric outside of a spherically symmetric object. But r equals r star is bad. If we don't get to r equals r star, we're good. Thankfully, if we're talking about the sun, unless you want to go way inside the sun and come back and tell us about it, we won't be testing that limit. So for the sun, we're ready to do physics, and we will. There's another problem. In classical physics, it's not a problem. We wrote this, and we have this, we say that this is not a problem because we know this is Cartesian written in a funny way, but there's another problem here. When r equals 0, what happens?
It's all undefined. Or, yeah, you go both go to 0. Because you have the lower part of the sun.
Yeah, the 0 here, 0 here. And forget it when you take the inverse metric. We know that the metric inverse has to exist. Again, last time I checked, 1 over 0 was not a happy place. Yeah? So, let me, for the moment, without giving any meaning to it, classify problems. I'm just going to call it singularities of the Schwarzschild metric. R equals R star and R equals 0. And now because I might use R equals R star. Hey, let's go evaluate this at R equals R star. This is not so easy to say. R equals 0 is easy to say. And we know evaluating things at 0 is a problem. So we want to, these are called singularities because, well, seemingly problems. As of now, they're just problems. Nonetheless, we will get to the source story very quickly, but I want to name drop so I can use the terms. Again, when I use the terms, you shouldn't think of anything more than just a name for them. So this is the true physical singularity. This is so that I can use the standard GR terms as I talk about things. Nothing, don't attach any meaning to it. This, let's just call it, is the event horizon. Because when I speak, I don't very often call it R equals R star. I like to say, hey, let's evaluate the event horizon. Why is it? Well, that's just cool sounding name. All right. What we want to do is, one more time, I'm just going to write this over here. 1 minus R star over R, C squared dt squared, plus 1 over 1 minus R star over R, R squared, plus R squared, beta squared, plus R squared sine squared beta. This is the Schwarzschild metric. These are the terms that are involved in the Schwarzschild metric as of now, so I can use them freely. Now we have to understand what this means. You will very soon see that space is not like X, Y, Z, and T anymore. There's something happening. But we have to slowly peel the onion layer by layer. And one way to probe space-time is to throw rocks at it, maybe beams of light in it, just to see how it responds, right? Like you drop a rock at it, all of a sudden you don't see it, something's going on. If you send a beam of light, and all of a sudden the beam of light does this and comes back to you, something's going on, right? Either way, these are all geodesics. So I want to analyze two types of geodesics. One is, of course, time-like geodesics, because this will be the path taken by objects that travel below the speed of light. And the other is non-geodesic. This will be the path taken by light in the space-time. So let's begin our analysis of time-like geodesics. We're going to solve the geodesic equation of motion without even solving the geodesic equation of motion. This is, so what is the geodesic equation of motion? Schwarzschild this is the geodesic equation of motion. Alpha tau dx beta tau equals 0. Hey, listen, you are fully ready to solve this geodesic equation of motion because you know what they are. I mean, solving it is a bear, but you know how to write it down. You know what gamma is, right? what is, and again, just to develop muscle memory, I know this is a mu, so I put a mu, and then I need a new index, and then I write 3 terms. The first 2 are positive, and the next one is negative. And so this is alpha, beta, lambda, beta, alpha. I know you may not be able to see, that's why on the video, that's why I'm reading it out. G alpha lambda beta, beta lambda alpha, and this is lambda alpha beta. And you can write this equation for mu equals 0, 1, 2, and 3. It'll be a bear. I'll let you, you will do it, but we won't do it in class. Once I give you the answer, I'll ask you to check one thing for me. In fact, I want you to calculate the theta equation eventually, because it has a story to it, a little moral. In physics, I say physics, in math, when you get complicated equations, you should look for conserved quantities. What conserved quantities usually do is help solve equations easily. I mean, if you have conserved quantities, you can expect useful things. Well, you can say, well, this quantity is conserved. Maybe we want to call it energy. And we will. But also, really the advantage is it helps solve equations. So to do that, we recall the Lagrangian technique. We saw that this can be written in this form. Yeah? And what was the Lagrangian? Well, it was just this. Yeah? But for a time-like particle, this is actually a constant. Can you tell me what that is? This is just u squared. So this is nothing more than minus e squared. For, I should write, for time-like. But we will look at this. Is this metric dependent on time? Do you see any t over here? Correct? That means this is 0 when mu is equal to 0. What does that imply? Correct? This is 0. That's derivative of 0 means this is a constant. So it saves us a lot of trouble. So I'm going to calculate. Let me write down L. It's sort of ridiculous to write down all of this over and over again because they are the same object. But now I'm going to write it as t dot squared plus 1 over 1 minus r star over r dot squared plus r squared theta dot squared plus r squared sine squared theta t dot squared. Correct? All the d phi and dr and d theta becomes dt d tau, dr d tau, d theta d tau, and d phi d tau. because of precisely this. So, for e's, because there's a squared, this is also conserved. If something is conserved, 1/2 of it is also conserved. What is that? That is minus 1 minus r star for r times c. Or I can write that as g t o, sorry, c t dot. And that is a constant. Correct? That is a constant. So I'm going to call that constant. This is negative, so I'm going to put it negative over here. I'm going to call it kappa. And then I'm going to do this. I'm going to multiply by -1 and mc for the throughout the equation. So mc kappa is equal to minus gtt, because I got rid of the minus. Then I have mc, and then I have c squared. Correct? I can leave this, but I want to give this a meaning, physical meaning. If I call it kappa, it's not so exciting. It'll be good that conserved quantity has a better name than kappa. So to get a physical meaning, I'm going to evaluate this as when the object approaches infinitely far away. As you go infinitely far away, what does minus GTT approach?
Oh, positive
1. So this approaches, so this quantity right here is 1. mc squared. T dot, look at this. U equals c t dot gamma u. Well, it's actually c gamma u. So T dot is nothing but, what is mc squared times gamma in special relativity?
Is that energy?
Yeah, it is energy. So this is the, I'm going to use epsilon because it's a tiny part. Epsilon for E, and E for energy. Therefore, I have an interpretation of kappa. Huh, Gracie.
No, I'm just happy I got it right.
The kappa is nothing more than energy per unit mass divided by speed of light. It just sounds better. So, what else? Which other coordinate does the metric not depend on? Correct. Phi. So when it doesn't depend on time, and therefore we have energy conservation. If it doesn't depend on phi, what do you think will be conserved? Rotation.
The azimuthal.
Azimuthal angular momentum. So,
Oh, but not all angular momentum is conserved.
no, only in the phi direction. And because of lack of space, what is that? I don't know if I put the 2 again. I did so it's this, I would get r squared sine squared theta phi dot is something conserved, but I'm not going to call this a new symbol. Instead, I'm going to call this m r squared sine squared theta phi dot. I'm going to call it L. L is for angular momentum, so you can see why. If you have something rotating like this, this is R sine theta. Angular z component is R cross P, so R is R sine theta. P is mass times velocity, and V is R omega. So m times r, r sine theta, times omega, which is phi dot. So when you multiply all of this, you get m r squared sine squared theta phi dot. See, this is the z component of angular momentum. So it's r cross p. This is r, this is p. Mass times velocity, v equals r omega. This is r, that's omega. Rate of change. It doesn't matter. It just gives an intuitive feel for it. So this is nothing but the angular momentum of the particle. And now look at what we have done. We have saved ourselves our metric can be written in the following way. I've got minus c squared equals, oh gosh, I have to, I know what t dot squared is. I know what t dot is. It's related to energy. This one is related to angular momentum. Here, kappa shows up. Here, L shows up. So when you put L and kappa, I would get minus c squared equals something. Okay? I mean, you replace this with kappa, this with L. But I'm going to do one more simplification. So I'm going to look at orbits, these geodesics. Now, if you look at a planetary orbit, if a planet's moving like this, it's going to stay in this plane. If it's moving like this, it's going to stay in this plane. Will it ever get out of a plane? Because of the spherical symmetry, will it push it out of the plane? So if I'm going to study equations, I know at most planets move in a certain plane. So what I'll do is I'll pick the most convenient plane there is. What is the most convenient plane? The equator.
Yeah, the equator.
Equator. So then I'm going to set
I guess R
theta dot equals 0 because I'm setting theta equals pi over 2. So this is problem number 1. It's just algebra. You will verify that when you set this to 0, replace this with kappa and this with L, you have a nice equation. And that is looks a lot like classical mechanics, except for a few additional changes. Kappa squared minus c squared. So you can see there's L here, there's kappa. Okay, sorry, there's L squared there and kappa squared there. So this is the equation you will verify. This is the geodesic equation that has r dot. Once we get r dot, we can get phi dot. And we'll see how. So problem number 2, this is problem 1. Problem 2 is use the geodesic equation. That one. To verify that theta equals constant is a solution. So when you put that, if you put r equals constant, it's not going to be a solution. An object cannot just necessarily stay there at the same radius. Yeah? But theta equals constant is a solution because we just assume that. So this is problem 1 and 2. So we can use this to understand how particles move. And what I'll do, I'll set it up for the problem that we're going to study. This will be the first, not necessarily historically, but for us, one verification. I'll provide 2 verifications for the Einstein equation. We've been immersed in math. It's good to talk about a couple of experiments. So in preparation for that, I would like to mention that r dot, well, this is just dr d tau. I don't care about how, at what time where the r is, but I want r as a function of phi. Is it doing this, or is it doing this, or is it doing this like a comet? That's what I'm really concerned about. So what I'll do is I'll write this as dr d phi d tau. Well, that is dr d phi dot, and I can write that as dr d phi L over mr squared. So r dot can be written as this.
Bm r squared sine squared theta.
Yes, what is sine theta? You're absolutely right, good.
Is theta still 0, or is it
Theta is pi over 2.
Pi over 2.
Sine of pi over 2 is 1. Yeah. So this, I must say, this is when theta equals pi over 2. Good catch. That's all we're concerned about. Now, the advantage of that is I can take this and stick it into this, and then you get problem 3. These are all just algebra at this point. This one does not. These two, this and this, does not even require calculus. You will see that d phi is equal to integral square root of a over r squared. Ooh, except I think I have it. A over j squared minus e over j squared minus 1 over r squared minus 1/2 dr. I just have to tell you what these a's and j's and all those things are. And they are where a is 1 minus r star over r to the minus 1. J is L over m kappa, sort of like angular momentum per unit energy, so to speak. And E is c squared over kappa squared. little bit of algebra. Because all I care is phi as a function of r, or r as a function of phi. I can integrate any which way I want.
Integral on the left-hand side too?
Yeah, sorry, yeah. So the first, I won't be able to derive this today, but let me at least describe what it is that we're going to do is, for many planets, it really doesn't matter. But for Mercury, Mercury is the closest to the sun. So if you have sun over here, so if you have Earth, this is what Earth is going to, well, I don't want to ruin the picture, but the Earth is going to do this. And then it's going to do this again. It's just going to go. But Mercury, what it does, it doesn't come back exactly here. Yeah? This is the closest point. That point sort of advances. Okay? The closest point to the orbit is called the perihelion. So what we do is compute the perihelion advance of Mercury. Now, Einstein worked all of this very theoretically, nothing to do with nature at all. Turns out the perihelion advance is 43 arc seconds per century. He gets that right.
Of course it
He just works completely geometrically. I don't even know if he did this sort of a calculation. Maybe he did.
So all the visualizations of that we've ever seen, they're all simulations then? Because
Yes.
we definitely can't see that happening.
No, 43 arc seconds, like
That's not even
36 hundredths of a degree in 1 century.
It's less than that, right? Well, no, it's 3600.
Yeah.
It's 1/60th of a minute.
Yeah.
Jesus.
In 1 century. And the dude gets it right.
He's the dude.
I mean, that
He always gets it right.
is the quintessential, right? Just sitting in an office and just cranking it up, telling nature how to behave. That's the calculation.